Melissa, whenever you're ready.
Okay, can you hear me? Can you see my screen all right?
Yes and yes.
Okay, perfect. All right, so basically going to be talking about the project I started last year, trying to do some implementation scale watershed monitoring to try and look at BMP efficiency in a couple of different watersheds in PA. But today we're going to be talking about pretty much all of Conowingo Creek's data. So this is going to be a very data heavy presentation. I tried to avoid some of the introductory stuff because data is what we all are excited about. But I'll just kind of give a general premise before I get into the meat of the presentation here. It's just kind of how the presentation is laid out today. First, I'm going to get right into the project, kind of what it is, the questions we're trying to answer, and kind of where we hope to go with it. I will share the preliminary data that I do have, emphasis on preliminary, because this is super early to be doing any kind of in-depth analyses, but I'll share what I do have. And then the early thoughts I have based on what I see so far, and then kind of where we hope to go with that in the future. So before I get into the meat of the project and kind of what it is, so we all know it's kind of a hot topic now, trying to understand if the BMPs we're putting in are working to the degree that we hope that they are. We just don't have the data right now to back all that up. We assume everything's going well because we do see changes happening, but we just don't know exactly what those reductions are that are happening on the ground. And so we started a pilot project to see, first of all, can we measure BMP efficiency on a small watershed scale as close as we can get to the scale of implementation as possible? So beyond the question of can we do this, period, some of the questions we're interested in trying to answer are, are those BMPs removing those pollutant loads that are being predicted by modeling platforms like Model My Watershed or others? And if they're not, or if they're doing better than we think they are, what's affecting the efficiency of those BMPs? Is it the characteristics of the BMPs themselves in terms of their size or where they're located in the watershed? But also land use characteristics, watershed characteristics, all interesting things that would tie into how well they perform on the ground. Beyond that, we would like to try to figure out how different combinations of BMPs affect water quality in different landscape settings. So do you have better results with more cover crops and riparian buffers as opposed to just stream restoration and fencing, those types of things? So we're starting very small with this. We have 2 watersheds we are prioritizing to sample a goal of 3 times during the growing season. Like I said, we're going to talk mostly about Conowingo Creek today because that's what we all kind of care about being in Lancaster County. But just know that I'm also working in other watersheds as well. So I'm also doing this in the Gadoris Creek watershed in York County, and then the Quittapahilla Creek watershed in Lebanon County. So in terms of what data we're collecting and when, so during the growing season, again, this is going to be a 3 times annual collection between the months of May to October. That's when we're going out to get our water chemistry samples and our flow measurements. That's going to be kind of the bread and butter data collection for this effort, because then we can calculate our loads for that point in time when that sample is collected. Now the water chemistry samples, there's a ton of different parameters that we test for when we collect them because this data is multi-use. It's not just for this project. But of particular interest to us, we're going to be looking at the total nitrogen and the total phosphorus as it ties into the BMP implementation. And then beyond that, we also take a set of field meter readings each time we go out. I'm also hoping to start incorporating some riparian vegetation components potentially down the road. I have a protocol I'm going to be testing this summer to see how it works out, if I developed it the right way, and if I need to make any changes to that. During the non-growing season, so this collection will be done every other year between November to April. That's when we're going out to get our macroinvertebrates. We're doing our habitat assessments on those reaches, and we're taking another set of those field meter readings. And by that, we're just doing our temperature, the pH, the conductance, and the dissolved oxygen. So in terms of where we're monitoring in the Conowingo watershed, so we have 10 sites throughout. And in the map on the right here, those are the yellow hexagons that are kind of sporadically shown there on the map. And they were located based on practice keeper data that I have on hand to try and put them above and below clusters of planned and implemented BMPs, as well as grant project locations. From there, it came down to where I had good site access and property owner cooperation. So that's kind of where we ended up in terms of locations. Now, each sub-watershed, hope you can see my cursor here, is associated with its, or monitoring point is associated with its upstream sub-watershed. So for example, this Conowingo 10 area here, this point, it's inclusive of the Conowingo 11 sub-watershed, but it's just kind of showing you where that break point is for the downstream limits of what this monitoring point is picking up, quote unquote. It's kind of like that throughout the presentation in terms of the graphics. So just kind of think of these watersheds as kind of layered on top of each other. And those lines are just showing you the downstream kind of like breaking points for each of those monitoring locations. So into the preliminary data part of this. Again, I'll emphasize preliminary. It's very, very early in this process to be doing this, but I wanted to get a superficial look at things. But also the process of analysis is in flux a good bit. That as it is, I've already changed this presentation as of yesterday. I went and updated all my graphs and stuff because I've been talking to some people and getting some feedback on how to properly look at this stuff. So it's going to be changing over time, but for now, this is where we're at. So the first thing I wanted to do with the data is get a feel for just how the watershed is behaving in terms of how it's changing with the yield of nitrogen and phosphorus going point to point as you move upstream to downstream. So I'm going to show a couple of graphics here in a second. So first I'll start with the table of data. So we have our chemistry sample that we take, which gives us our concentrations. And we have our flow, which gives us the ability to calculate a load in pounds per year for that particular point in time. And then we take the average of that to use in these calculations. And to get our yields, that's where you divide by the subwatershed size to kind of standardize it so you can compare them throughout the watershed, kind of apples to apples basis. And then from there, we can kind of look at how those yields change as you move upstream to downstream. So it's as simple as taking the downstream, subtract out the upstream, and get a net change number, which as a heat map kind of looks like this on the right. So areas where it's a darker red, we had increases in the yields going upstream to downstream. Where it's lighter, more this neutral gold color, that's kind of your zeros, or sort of a reduction in the yield between the upstream to downstream. So looking at that, is kind of neat to see kind of where those hot spots are and kind of where the changes are happening in the watershed. And it's also interesting to kind of look at how the tributaries kind of play into this too, because that can kind of be a little bit tricky to look at. So notice we had a net change of negative 21-ish pounds per year per acre at this Conowingo 6 point. And you have to kind of think of it as you're combining two things. So you have your tributary over here. We know the yield coming in from here. We know the yield from here. That's kind of our upstream part that we're comparing to the downstream measurement. So that's why it kind of looks like it's a pretty big jump, because something's happening here where it's mitigating or reducing that yield in this area, even though it's kind of heavy coming in. And you see something kind of similar the downstream end. So Conowingo 2 is super, super little down here. It's hard to see, but it's roughly about 300 to 400 feet downstream from the confluence of the Little Conowingo and the other main stem site from Conowingo 3. So again, we know what this yield is coming in here, and we know what it is coming off the side. So we combine those two to get our upstream measurement to compare to, and so that'd be about 56 pounds per year per acre between those two. And at Conowingo 2, we're only measuring about 29.1. So that's pretty interesting to see too, where something at least is happening between those areas to mitigate, potentially reduce those yields coming off the landscape. So we do the same sort of thing with the phosphorus yields to look at those. So there's the table with the data there, and I did sort of a different color of heat map just to as a visual reminder that we're talking about a different pollutant here. So the darker blues are the increasing yields between points, and the more neutral kind of aqua colors are like the zeros or close to zero. The green is the negative changes in the yield. So again, you see sort of the same thing with the confluence of where tributaries come in versus what the downstream side is showing you for the yields. I'm seeing some type of buffering or reduction potentially happening there. And then same thing at the downstream end near Conowingo too, where we're kind of seeing something going on. We'll see if this changes over time once we have more data to add to this. But it's something we're going to be watching and using to evaluate what's going on. So now I kind of had an idea for what was happening, kind of point to point, those types of changes. I wanted to relate that, of course, to BMP implementation because that's the whole target of what we're trying to look at. But before I could do that, I had to come up with some kind of combined metric or a score that was kind of unitless that we could use that was standardized to compare it throughout the watershed, similar to using yields for the nutrient comparisons. So those of you that are familiar with Practice Keeper know that there are 3 different geometry types in there that you can use that have BMPs assigned to them. So, and each one can have different units. So I wanted to find a way to combine all of that and use all that information. So what I did was I took the list of Practice Keeper BMPs, the unique types, and I looked at what I could use from the Model My Watershed spreadsheet tool to actually model reductions and tried to assign a Model My Watershed BMP to the Practice Keeper BMP that made the most sense, to just get some kind of basis to create a score off for each of these types of practices. So once I had those assigned, I went through and into the spreadsheet, created the Model My Watershed generated inputs for the Conowingo watershed, and then went through and experimented with each BMP type to figure out how much of that particular BMP would be needed to reduce 1 pound of nitrogen. So you have a raw nitrogen score, and to reduce 1 pound of phosphorus, you'd have a separate raw phosphorus score. And I decided that for every pound that would be reduced by whatever quantity of that BMP, 1 point would be added to the score. Now, inherently in doing that, there are unit differences between what the Practice Keeper BMP unit is that we start with and the Model My Watershed one that was kind of assigned to come up with some kind of score. So when that happened, I had to figure out some sort of Model My Watershed unit equivalent that I could use to then calculate a score from. So, for example, there's a lot of linear features in Practice Keeper that I had to come up with a way to model as an area to come up with something similar to it. So in that case, I just assumed, okay, well, for every linear foot of fence, I'm going to assume 1 square foot of area to come up with an acre equivalent to use. So once you had those equivalents, then I could multiply, okay, I have my BMP amount from Practice Keeper, multiply it by the equivalent that I need to get what I'm going to use to create the score. So once you have those, then you can take what your scoring amount was for nitrogen and for phosphorus, and divide it by the amount you would need to reduce 1 pound to give you the number of points awarded for that particular BMP practice. So you had all these raw scores now for each type of BMP, for nitrogen and for phosphorus. So then for each subwatershed, you add up all the raw scores for nitrogen, all the raw scores for phosphorus. As you can imagine, as you got further downstream, that score got to be quite high. So I wanted to make sure again, we're standardizing for the watershed size. So I took the raw score, so the points that were assigned, and divided by the area of the subwatershed to give us a points per acre number to use. So even though it's technically kind of a unitless system, it essentially also kind of means something. So the score is equivalent to the pounds of nitrogen or phosphorus that are reduced per acre, essentially. So that's kind of just a general walkthrough of how I went through, assigned all that, and where the scores kind of came from. I'm not going to show you all those numbers, but that's just a narrative of how that worked. So now that I had those and I had scores for each of these subwatersheds, now I could take that and kind of look to see how that is lining up with the yields and how they're changing upstream to downstream. So I'm going to show a couple graphs in a second. But before I do, so the things we're going to be looking for are kind of the subtle changes. So what's happening on a point-to-point basis, upstream to downstream with the yield, and how that is also changing with the score for nitrogen specifically in this example. So on the left, there are two graphs. On the x-axis are the monitoring sites. As you go left to right, it's upstream to downstream. The top graph on the y-axis is the average nitrogen yield for that particular site in pounds per year per acre. Error bars represent the standard deviation of the data, so you can tell there's a ton of variability. We only have 3 sampling events, it's only 1 year. But looking at the averages is still kind of interesting to see kind of what we might be looking at down the road. You also notice there's 3 different point types, so most of the dots that are connected there, those are the main stem sites. But remember, we also had the unnamed tributary come in, and we have the little Conowingo. So I tried to arrange them linearly to where they would kind of come in near the main stem. So it kind of made sense looking from left to right. And then below that is just the nitrogen score for that particular subwatershed, again, as you go upstream to downstream, left to right. So I'm going to walk through a couple of points and just kind of give you an idea of what I was looking at that kind of looked interesting to me. So we'll look at the first set of points starting in the headwaters. So going from Conowingo 11 down to 10, if we look down below the nitrogen score, we had a little bit of an increase in the score when you compare downstream from upstream. And if you look in the above graph, you'll see we had an increase in the yield still, the average yield, despite an increase in the score. Looking a little bit further downstream, going from Conowingo 10 to 9, you'll see we had a bit of a jump in the nitrogen score there. And the yields kind of flattened off. It didn't really increase a whole lot. It increased a little bit, but not by a lot. And then kind of moving more towards the middle of the watershed, this is kind of where trying to incorporate those tributaries gets a little strange. But if we look at the main stem sites, so going from Conowingo 8 downstream to Conowingo 6, we had a little bit of an increase in the score, and we had a decrease in the yield. You'll also notice that the score for the unnamed tributary was the highest in the entire watershed, and it also had one of the lowest nitrogen yields on average. And then moving all the way down towards the mouth of the stream. So if we look going from, so Conowingo 3 is a little bit outside of that red line to the left, but from there downstream to Conowingo 2, the score really doesn't change a whole lot and doesn't change much for the little Conowingo either. But the yields are decreasing just a little bit on average between those two sites. So interesting to look at. Did the same sort of thing for phosphorus. So these are the same graphs, just with phosphorus-specific information. So again, I'll kind of walk through these points a little bit. So phosphorus score in the headwaters was also pretty low, and we had a decent increase in the average going upstream to downstream. As we move a little bit further downstream, we had an increase in that score, had a little bit of a decrease in the yield going upstream to downstream. Again, looking in the middle, a little bit of an increase in the score. Again, that unnamed tributary had a very high phosphorus BMP score, not much change in the yield there. And then going all the way towards the downstream end from the little Conowingo into downstream site Conowingo 2, we had a little bit of a decrease in the phosphorus score on the main stem site, and a little bit of an increase in the yield. And then the little Conowingo tributary, we had a little bit of an increase in the score going upstream to downstream there, but we had still an increase in the yield. So that's kind of just generally kind of what I'm looking for. And while these subtle changes are interesting to look at, I was curious as to how actually significant they are at this point. So I asked myself, how does that net change that we were looking at earlier relate to the scores that are assigned to these watersheds? Is there any relationship there? And the answer to that is not really right now. The model we have right now doesn't explain a whole lot. P-value is not good. We don't have enough data to tell you anything about what your score would have to be in order to see either a reduction in the yield or just kind of a break-even point. We need some more information. We have a lot of outliers that are kind of skewing where this model sits at right now. Same thing for phosphorus. Not a great model. We have some outliers that are affecting where that sits. Doesn't explain a whole lot. P-value is not good. And I really can't give you a break-even point there either, or when you might expect to see reductions. But aside from this, there are lots of other factors at play that we want to incorporate down the road. And one of the big ones is land use, right? So we all know how important land use is to water quality. The chart on the right here is just a generalized view of the land use for each of the subwatersheds in the Conowingo. And you'll notice that some of these numbers have stars on them and they're in different colors. What that basically means, if you were to take the average of that particular land use type for the whole watershed, it would tell you that that sub-watershed's type of that land use is different from the mean. And the color of the star tells you whether it's a good or a bad thing for water quality. So for Conowingo 11, for example, seemed to have a lower percentage of agricultural land use compared to the rest of the watershed. So that's a good thing for water quality. And then its urban land use, as you look towards the bottom, seemed to be a bit higher than the average, which is not such a great thing for water quality. But in any case, these are the kinds of things that we want to try and incorporate into this somehow. But also characteristics of the BMPs themselves. We haven't gotten into that level of detail yet, but I'm hoping to, and hoping to learn some interesting things about what improvements we can make to improve their efficiency if they're not performing as well as we would like them to. But also be interesting to do sort of the time lag understanding of how long does it take from when you implement a particular type of BMP to when you start to see those reductions happening. So some early thoughts based on what I see so far. And this isn't groundbreaking stuff. This is stuff we hope to see, what we expect to see, but we don't necessarily have data to back it up. Is that increased BMP implementation can be buffering or reducing those increased yields as we go downstream. And like I said earlier, as we collect more data, hopefully that relationship will be more clear and we might be able to say a little bit more about that. But then again, too, reductions might not be happening yet in some areas. We saw yields tend to increase upstream to downstream in most cases. But there's a lot of other factors at play, like I said, that could be affecting the inherent ability of those BMPs to reduce nutrient loads. And that could have things way beyond the control of what the BMP is able to do. Soils, geology, presence of other pollutants in the water column. I've seen a few talks where they talk about chloride and how that may affect the mobilization of nutrients from soil into the water. So those are kinds of things that we kind of are interested to take a look at and see if that's playing into any of this. So where we're going, well, we have a lot more data to collect, a lot more work to do, as I'm sure you can guess. But down the road, once we get a good enough data set, that's where I want to start to do the more in-depth analyses, updating and refining those yield response estimates, maybe looking at other pollutants to see if that has anything to do with that. I also want to start comparing our monitoring data to modeling platforms to see how close to the mark are we. Can we use, the modeled estimates as a good benchmark and an estimate? I mean, we just don't know how good those estimates are right now. And then beyond that, if there's another story to be told aside from the chemical part, which could take a long time, can we instead tell that story with the biological side, looking at macroinvertebrates or looking at riparian vegetation? All those kinds of things that we're hoping to be tying in and bringing into this analysis. So that's all I have for you today, but I want to give a huge shout out and thank you to everyone who's helped me in the field. I know some people from the Lancaster Conservation District have come out to help me, which has been great. A lot of my staff have come out to help me. And thank you guys for having me today. It's a pleasure to talk to you. And with that, I'll I'll take any questions, and I'll leave my contact slide up here as well.
Thank you so much, Melissa. It looks like we've already got a question in the chat from Brian, and Mike also has his hand raised. So if you need me to read anything from the chat, I don't know if your screen sharing is making that a little wonky, I'm happy to do that.
I'll look at the chat here. Curious how attenuation is being factored into this. We found how we scale our basins. Model watershed have significant influences on modeled loading. Some of the smaller basins don't often match a single basin comprising all of them. Yeah, so the attenuation question, I'll be honest, I don't know that I've gotten that far yet. That's probably a whole other element I need to figure out. Like I said, the analysis itself is very much in flux at this point. I don't have a good answer for that at this time, but I'd certainly be willing to ask you a bunch of questions about that, Brian, if you have a lot of experience, because I'm going to need some help to make heads and tails of what's going on. Okay, great. Any other hands up that
Mike,
you
if you
can
want to go ahead, you had your hand raised.
Sure, thank you, Melissa. Just out of curiosity, some of those other models you're going to look at, does that include, do you think, the USGS Sparrow maps? I'll be honest, at times, if we're encountering a new site or we're looking at an area, we'll usually, as a quick reference, check out the mass loading and incremental loading maps out of the USGS, since they break them down by catchments and watersheds. It's just a great quick reference. But there's times we've looked at them and said, I'm not sure about that, if that's actually what we're seeing. And it just seems the way you've got things set up, it almost would appear could ultimately validate or calibrate both the mass loading and the incremental loading maps.
Yeah, it's certainly something I'd like to do, because there are several models out there, and Sparrow is one of them that I was kind of playing around with the idea of looking at. Another thing that's important to distinguish with this project as opposed to the important work the USGS is doing is storm sampling is not part of this. This is looking at ambient conditions only.
Mhm.
So especially with the phosphorus, I'm not sure how much my work is going to be able to help with that, but I think the nitrogen would definitely be meaningful, because I think even at base flow, nitrogen's a pretty stable thing, from what I've heard. So it's definitely on my list of things to look at, yes, with the Sparrow.
Great.
I also have a few questions, Melissa.
Yeah.
First was, how long do you plan to do this study? So when did it start, your like first round of sampling, and how long is it planned for, at least right now?
So I started in May of 24. So just started. So we're coming up on, we had about a year of sampling done. Well, I'm hoping to just keep doing it for as long as I can, a minimum of 5 years, hopefully longer, to try and get some really good data, because 3 times a year is pretty good, but I mean, it's still a pretty limited data set in and of itself. But it's hard, I'm the only biologist in my bureau that does this. So like a one-man army out there trying to take care of all this. But yeah, so it's going to go on for a good while, I hope.
And so with that timeline, I'm like, you expect to see new BMP implementation within your area of study and kind of track how that changes over time as well, or just, be able to factor in those new projects?
Yeah, that's the hope, is that as time goes on, now that we started this, we sort of have quote unquote baseline conditions for before some of these BMPs went in, and now we can start to see how things are changing as stuff goes in. So that is definitely part of the plan, to see how things are changing with that.
Great. This was really interesting. I know for myself, I took a lot of notes there. Super excited to see how this, keeps hashing out in the next couple of years. And I appreciate you sharing everything, even though, like you said, it all seems very early and preliminary, but it's very, very interesting. So any other questions for Melissa?
No, but this was super exciting to listen in on, mostly because the program that I'm working on also recently started, and I think Conowingo 6 site is very close to one of ours. And we
Oh, very nice.
don't take any nutrient data, and some of what um like we just don't the monitoring takes 4 hours. We can't add things to it. So we would love maybe eventually down the line to see if we can do some comparing notes on some of the data that you have. We do have pre-2024 data, but we are missing like some benthics, and it'd be so cool to see what's going on above the watershed as well, for some of the data you've taken. So super excited that you're working on this, and it's something slightly different, but hopefully can like inform some of the work we're doing. And yeah, it's very cool.
Yeah, great. I'll definitely try to connect with you on that.
Yeah, I grabbed your email, so I'll probably be in touch sometime this month. I'm out all next week, but yeah.
Perfect. Awesome.
Great. Anybody else before we move on? I think you could also throw something in the chat as message to Melissa or grab her email or anything like that. So I will pass it over to Katie Bartling now to share some of her work.
Sounds good. I'm gonna share my screen. All right, can you all see my screen okay?
Yep.
Okay, great. All right, we're gonna get started. So this presentation is going to also be focused on a lot of data that we've been collecting along with many partners in the Kanawha watershed. And this is a PSU synaptic sampling program, synaptic meaning comprehensive throughout the watershed. And it was really meant to complement some of the other data that's being collected in Kanawha. So I just want to touch on that as part of Penn State University Ag and Environment Center, we are running under a NIFWIF grant, the National Fish and Wildlife Foundation grant. And this is the new Lower Susquehanna Regional Partnership grant that we have. And one of our biggest goals is to facilitate the existing and emerging watershed partnerships. So we're going to provide venues for intentional collaboration and directed meaningful watershed community engagement. So we have a lot of pieces to our NIFWIF grant, but one of them is to help all partners to accelerate implementation of BMPs on the ground. We also have summer internship programs, and one of our latest endeavors is to move beyond the choir, we're calling it. We're working with Kathy Brazier, who is a professor of rural sociology in the Department of Ag, and the Interfaith Partners of the Chesapeake to build capacities with faith communities. And so I just placed this map here to show our geography. So the AEC really started in Chickees, Kenoi, and Conewago, and now we've expanded into Little Conestoga and some of the other river tributaries, and then up into Spring Creek. So we're helping to sort of develop those watershed partnerships as well. I just wanted to touch on some of our developing projects in all these watersheds, and especially in the Conewago, which is where we're focused today. But just some of the projects are Arm Farm Nutrient Trials, which is with Charlie White's lab at Penn State University, and they're really working on taking actual nutrient analysis on farms to help understand how much fertilizer is needed for side dressing for farmers, so that can really reduce their application rates, save them money, but also reduce the nutrients that are going into the bay. Surface water age dating analysis, this really gets back to lag time in some of our watersheds and understanding the accumulation of nutrients from groundwater. And so we're starting tritium analysis in the Conewago. And an eDNA pilot study is also in the works with our critical initiatives at the SAFES Institute, which is what I'm a part of, the Sustainable Food, Agricultural Food and Environmental Science Institute. And then our GIS team is working on prioritization dashboards to try to help our farmer liaison and farmer outreach professionals to know, where to go next in the watershed and who to talk to. And then, of course, with our interns, we're continuing our windshield surveys and tillage surveys. And these are projects that you all probably have heard of. Okay, so today we're going to be talking about the Conewago. We'll walk through a little bit of the Conewago Creek Initiative, just very briefly, because I think all these folks on this call really know about that. Watershed overview, the whole water quality program, and then I'll get into the data for our synoptic sampling. This photo here is a Londonderry Township Conewago Restoration MS4 project, which incorporated a large legacy sediment removal and floodplain restoration. All right, so Conewago Creek really spans 3 counties. If I could move this. Yeah, 3 counties. So the watershed is 53 square miles, and it's predominantly ag land use, so about 42 to 53% ag land use. I wanted to point out, since we were talking about salt watch, there's major roadways in this watershed, and you'll see in the data later that we did get salt and chloride hits from those locations near these major roadways. There's about 110 miles of stream within this watershed, and the majority, though, are first order headwater streams. And so that the headwaters start in Lebanon County and they flow southwest along the main stem of the Conewago into Susquehanna River. All right. So Commonwealth protective uses, we have water supply, recreation, and aquatic life use. I wanted to point out some of the locations of our impaired waterways. They occur along the main stem of the Conewago, Hoffer Creek, Gallagher Run, Lynch, and First Tributary North. Aquatic life is trout stock streams, and the upper reaches of this watershed, it supports a cold water fishery, and then slowly gives way to a warm water fishery in the middle portion and lower portion. Impairments are attributed to sediment and nutrient loads and runoff. So these are 2022 aquatic life use impairments. It translates into the most recent 2024 as well. So to sort of combat some of these impairments, there was an understanding within the community that a local watershed group would really help facilitate some of the restoration that was needed. And so in 2001, the Tri-County Conewago Creek Association was formed with local residents, and it has been expanding over the years. So in 2020, the TCCA received the grant funding from the 319 program to complete watershed assessments and restoration plans through a consulting company. And then in 2022, 6 projects are underway with 319 grant funding. And then also there's the Conewago Creek Initiative, which is a large partner-based initiative. We continue to have regular meetings, and it really started in 2009. It's multi-sector and really based on improving BMP implementation rates. So we probably already all know this, the TMDL in the Conewago. It was one of the first watersheds in Pennsylvania to acquire a TMDL, and it was really focused on phosphorus. It's generally the limiting nutrient that was considered in this watershed. And the 2006 TMDL focused on ag impairments. So largely based on the assumption that phosphorus is mostly attributed to the cropland and row cropping and ag land use in the watershed. And then the 2021 WIP, the Watershed Implementation Plan, really helped us at AEC focus on some of our priority watersheds, Lynch Runs, Brills, and Hoffer Run. All right, I just wanted to touch on that. Conewago is part of a large, broad, long-term water quality monitoring program, which is exceptional. It's offering us an opportunity to have collaborative data sets. But I wanted to point out that USDA, NRCS, Chesapeake Bay showcase watersheds were established in 2009, and so we have that running data set on the Chesapeake Bay programs database. And then we also are part of at PSU the long-term agroecosystem monitoring, which is LTAR for short. And there's 4 watersheds shown here: Conewago, Mahantango, Spring Creek, and Anderson Creek in Pennsylvania. And the LTAR was developed to study multiple agroecosystems like cropland and grazing land and integrated systems. So here in the Conewago, we're part of an integrated system, production and crop forests and feed forage, grazing and feeding, and also manure handling. So that would be an integrated system. And that's what we are focused on here. Penn State University got involved to help with the LTAR in 2019 and to partner with USDA Agriculture Research Service. So all of those samples end up actually on Penn State's campus where the ARS lab is located. And really, like, these long-term data sets are focused on exactly what we always talk about: is there's so many factors that impact water quality. And this is a really good diagram. I also wanted to point out, like, John Clune had a big hand in helping Penn State get more involved in some of the sampling in the Conewago. He was previously with USGS and now is at National Park Service as a hydrologist. But yeah, physical factors, there's source inputs, there's legacy storage. The legacy storage question is where we're trying to get at with some of our tritium analysis in the Conewago to understand the actual age of the water that's flowing through the watershed. And another great diagram from a recent presentation that John Clune had developed with USGS is just understanding, like, what we were talking about between concentrations and yields and then loads. So with our synaptic sampling, we're really talking about concentrations. So that's mass in a known volume of water, it's milligrams per liter. And to understand yields, what Melissa was talking about, really, and then also understanding the data from the Chesapeake Bay Watershed Data Dashboard. Like, this really was the impetus for starting the Synaptic program, because comparing watersheds within the 5-year period of 2016 to 2020, the Conewago watershed at Falmouth had the highest yield score results in the 5-year period. And so we really wanted to start a more comprehensive sampling program within the watershed. And that really started with John Duncan's lab at Penn State. So grab water sampling. So as I mentioned, that includes the LTAR program and then our synaptic sampling. Grab water sampling also occurs at the USGS stream monitoring locations, along with some of their continuous monitoring, in-stream monitoring devices. And then Susquehanna River Basin Commission also has data within the watershed, and the macroinvertebrate sampling occurs under 3 entities here that I have. Fish surveys with Susquehanna River Basin Commission and the conservation districts. And then we also have district data. So in Conewago, I just wanted to point out that we have a long history of monitoring here with many partners. All right, so touching on our partnership work with Penn State and USDA and USGS, here are our locations on this map here. So the USGS gauge stations, we have 3, and the one that is located in Lebanon County, which is Little Conewago, is the gauge that I mostly have most connection to, because we assist USGS with the monthly sampling there to sort of collaborate with their in-stream monitoring device. And then there's 2 gauges in Dauphin County, Bel Air and Falmouth. So all of these gauges are online, and for Little Conewago especially, you can get live nutrient data because it is considered a super gauge. So it's part of the water quality WQN network. It's a non-tidal network. And so you can get live nutrient data on the website. One other thing I wanted to point out is that the LTAR And stream gauges, USGS stream gauges, are mostly in more of the ag pieces and portions of the watershed. And so with the synaptic sampling, these black dots here, it's more of a comprehensive look of in the headwaters and small tributaries to try to get an understanding of some of the hotspots or increases in nutrient loads that we're seeing on the stream gauges. So it was really meant to complement this other data that's occurring in the watershed. So synaptic sampling, a lot of you on this call have helped with Penn State synaptic sampling, and we appreciate your support. We really cannot do it without volunteers. And so it's an opportunity to network. Penn State has interns in the summertime, and so they always get involved and they're able to network with some of the other entities that are working in our watersheds. And you're just able to talk about your projects and have a nice day in the field. And so we gather around 9 o'clock and then disseminate across the watershed to sample at these locations within a 1-day period. So synaptic sampling is 30 locations across the watershed, and there's a history since 2020 of this data set. Some locations have a longer data set than others, and that's just based on access and volunteer availability, honestly. So at one point, there was a bridge down at Aberdeen Mills, and so that location doesn't have as long of a sampling history, for instance. There's 15 locations of synaptic sampling on the main stem Conewago, and then others are really included along tributaries. This required a lot of work for accessibility to the locations and working with landowners and continued, relationships with those landowners to continue to have access to the sites for sampling. And so there's major roadways likely contributing to the high chloride hits that we're going to see in our data set. So synaptic, all these samples go to the Penn State John Duncan Lab on main campus, and this sampling program started out of a USDA AFRI grant, and we really wanted to relate to the 2018 Sparrow data set that John Duncan had been observing. And we try for quarterly sampling effort. That's based on if we can get everyone together. And we also try to sample at base flow. So again, just like what Melissa was saying, this sampling program does not involve storm sampling. In the Conewago, however, we do have storm sampling through our partners at USGS and SRBC who are doing some of the storm sampling. SRBC conducts that at the Little Conewago site. And so, so this is the data that we really analyzed for. And today we're just going to be looking at nitrogen and phosphorus and chloride measurements. So let's see. So I wanted to point out that this data set is continuing to be collected. And so we have a whole year of data from 2024 that is still in analysis. And so we're going to be QA/QCing that and then getting it into our database here. So this data only covers up until 2023, but we have orthophosphate data here showing from that time period. And I wanted to point out that in the full data set, the minimums and maximums for orthophosphate are posted here. And site 28 really turned out to continuously have high hits. And so I wanted to sort of compare this data set. And so there was a US EPA, USGS National Water Quality Assessment, and it compiled data from 132 stream sites in the watershed where ag was also predominant. And between that time period, the majority of those stream miles that they studied displayed orthophosphate as P, which is what you can see here in the table above. The majority of the sites had less than 0.1 milligrams per liter. About 40% of those stream sites had orthophosphate as P results between 0.1 to 0.3. And then less than 5% of those sites exhibited higher than 0.3. And so at site 28, that's sort of where we are in comparison to that USGS EPA study. 0.5 was the maximum there. And then the averages, which is what is shown on this map here, it's averages per location. So it's taking all the data from the up until 2023 and averaging those across the seasons. So I want to point out that across winter and summer, all of those averages are placed together. And site 28 still came up as a hit, which is up here in the headwater reaches. And the average maximum there was 0.1. So the average wasn't super high, but it still came out as the highest. And then we also have a location in Hoffer Creek that is coming up as one of the highest averages over that time period. All right, and so now to get into nitrate as N results, nitrate nitrogen, it presents data it's combined with the nitrate ion. So it's nitrate nitrogen. And so that's the data set that we're presenting here, mainly because there's a drinking water standard for nitrate as nitrogen. We all know probably it's 10 milligrams per liter. And so that's sort of a gauge that we can go off of. There's no real surface water standard for nitrate as nitrogen, but we can use the drinking water standard. And so the results here, so site 28 is low for nitrate as nitrogen, but the highest results that we got are in Hopper Creek and Gallagher Run. And the maximum is at site 14, which is down here at Gallagher Run, and that was at 8.3 milligrams per liter. And then averages per location, the average min was 0.6 and the max is 5 at site 14 as well. So now we can understand that site 28 is really high for phosphorus and site 14 is really high for nitrate as nitrogen. That same EPA USGS study was sort of used for us to gauge what this data really meant. And it was from 1992 to 2001 again, and it was 132 streams. So, and about 35% of those stream sites sampled exhibited nitrate as nitrogen between 2 and 6 milligrams per liter. Around 10% of the sites in that study had results between 6 and 10. And so we're sort of in that area of the 35% of the stream sampled. So we're sort of fitting in with that data set, 35% range. Yeah. And so we also wanted to look at seasonal fluctuations and headwater streams. And this also is a site slated for the age dating analysis and to understand groundwater flows. And so the results here, nitrate as nitrogen is higher typically at base flow in the winter. And that's most likely because the source then is groundwater and it's lateral flow and seeping into the stream system. So also during this time in the winter, biological activity is lower, so less is consumed and used by organisms. And we can see the results here from site 19. We do have slight increases in the winter time, especially during the January location here, January 11th, 2021, we have one of the highest hits of milligrams per liter. And so we're still understanding this, we can't say for sure, but that's why we're continuing to study this site to understand this headwater reach and this small tributary and how it's contributing to the larger influxes downstream. And since Amanda had brought it up, I was glad that I included this in the results. So these are chloride results from synaptic sampling, again, showing average per locations for all events. And so you can see definitely that near the road crossings at Gallagher Run and Hoffer Creek, the salt application on major roadways and highways is likely contributing to these increased results that we're finding. There's also a community wastewater package plant near Site 16 that is likely contributing to the high hit there. And so I think that's all for now. I just want to put out a call for volunteers. We have an upcoming synoptic sampling and it's coming up quick. And we just decided on it today, but we need as many volunteers as we can get out into the watershed. So I know wintertime is not as desirable as like May or summertime, but it's still a really fun day to get together and sample it within a team. And to collect really important data for the Conewago. So we have a synoptic sampling coming up on Tuesday, February 18th at 9 a.m. And so I'm going to send out a call for volunteers and a calendar invite today. So yeah, thank you for asking me to present today. And if anyone has any questions, feel free to reach out or ask them now. And thanks for listening.
Thanks so much, Katie. Yeah, I'll open it up and give everyone a minute to ask any questions. I do want to say, Katie, thank you so much. Just kind of, I think it's so important to get a reminder and kind of an overview of all the different programs and work going on in the area in the county. And so that in itself is super helpful and just also really interesting to hear about the data that you guys are collecting. And yes, everyone join Katie on next Tuesday.
It's Shannon. This is Jamie. I had a couple of questions for you, Katie. Appreciate the overview. There's a lot of stuff obviously going on in your study, and my question is more curiosity. Like, do you guys have a document, or is there something that has the information in your presentation that makes it available for those of us who want to dig into it? I had a couple of specific questions. You know, you presented on all the different nitrogen forms that you guys are testing for, and I'm always curious about the relationship between nitrate and other forms of nitrogen in stream water, and especially how that may pertain to some of the management practices that are being implemented on the landscapes.
Yeah, so I, did prepare this slide deck in more detail for other presentations, and I'm of course happy to share it. One thing I can also share is a GIS geodatabase that I've created to sort of combine all these data sets and create overlays. And so, yeah, that is, I'm happy to share that as well. This is really based off of the lab sampling with John Duncan's lab. And so it is a comprehensive sampling protocol, and that Melinda Marsh is really spearheading in John Duncan's lab. And so I can ask her if she has any presentations or any other formats for data sharing as well.
Okay, yeah, that'd be great. And appreciate it. I don't know if we'll be able to field anybody. I'm on leave next week, but I know that in the past we've tried to join you guys for your synoptic sampling. We can also shout it out, at least through our social media. I don't know if you want if that's helpful, or if you're looking for folks who can bring their own gear and experience.
That's absolutely helpful. Yeah, I can send you the call for volunteers here. Yeah, I would really appreciate that.
Okay. Yeah, I'll pass that along to Stacy. Thanks.
You.
Appreciate that. It was an interesting presentation, Katie. Thank you.
Great. Yeah, thank you, Jamie.
Any other questions for Katie? Like I said earlier, you can always throw something in the chat, grab Katie's email, anything like that.